Chapter 9, Section 4, Inner Product and Vector Norm. In this section, we will explore why the relationship between inner product and a vector norm is important. Key properties of norm. Various types of norm and how the choice of norm type affects vector evaluation. So far, we've studied dot products and their generalization, inner products, which enable us to understand the directional relationship between vectors. But in working with vectors, it is not just the direction that matters. How large a vector is can be just as important. That is where norms come in. They give us a precise way to quantify a vector's size. There is also a strong connection between norms and inner products. In Euclidean space, for example, the norm of a vector can be defined using the inner product of the vector with itself. Understanding this connection enables us to deepen our grasp of the structure of vector spaces. Let's begin by reviewing what a norm actually is. In a vector space, a norm is a function that assigns a non-negative real number to each vector. This number represents a vector's size or length. Mathematically, we write it in this way. Here, v is any vector, and v with double vertical bars is the vector's v's norm. Norms enables us to make quantitative judgments about vectors. Which vector is larger? How far is it from the origin? This is essential in analyzing the geometry of vector spaces. For example, to determine whether a feature vector is an outlier, we might examine whether its norm is unusually large compared to a threshold. Norms also play a key role in defining distance. The distance between two vectors, u and v, can be written in this way. This is simply the norm of the difference between the two vectors, which gives us a measure of how far apart they are. The Euclidean norm aligns closely with our spatial intuition of length. For a vector v, the Euclidean norm is defined in this way. It gives you the straight line distance from the origin to the point represented by the vector. What is especially important here is that this definition can actually be expressed in terms of the inner product. Recall the definition of the dot product or inner product of a vector with itself. This is exactly the squared length of the vector. This shows that the Euclidean norm is derived from the inner product. Next, let's explore key properties of norm. Positivity and non-negativity. Scalar multiplication. Triangle inequality. Let's look at the first fundamental property, that any norm must satisfy positivity and non-negativity. This property is quite intuitive. For any vector v, its norm must satisfy the following conditions. Non-negativity. The length of a vector can never be negative. Positivity. The norm is zero if and only if the vector is the zero vector, that is, all its components are zero. This makes perfect sense when we think about how the Euclidean norm is defined. Since it involves squaring each component, every term is non-negative, and the only way the total can be zero is if all terms are zero. This also aligns with the non-negativity of the inner product we learned earlier. In short, positivity and negativity ensure that the norm behaves in accordance with our geometric and physical intuition of length. Let's now turn to scalar multiplication. The scalar multiplication property is so-called homogeneity. For any scalar C in R and a vector V, a norm must satisfy this equation. This means that if you scale a vector by a factor of 2, its length also doubles. However, since norms are always non-negative, we take the absolute value of the scalar. This property is essential for understanding how norms preserve linear structure and geometric consistency in vector spaces. Next, we have the triangle inequality. This describes how norms behave with respect to vector addition. This expresses the idea that the direct path between 2 points is shorter than or equal to the path that goes through a third point. This property is also essential for understanding how norms preserve linear structure and geometric consistency in vector spaces. It is a fundamental principle of Euclidean geometry. In any triangle, the sum of the length of two sides is greater than or equal to the third side. We can visualize this with a diagram. Draw vectors u and v as arrows starting from the origin. The vector u plus v then becomes the diagonal of the parallelogram formed by u and v. This inequality enables us to compare distances and proximity using norms, an essential tool for tasks like measuring how far data points are from each other or from a cluster center. We have already seen what the Euclidean norm is. It is also called L2 norm. While the L2 norm is intuitive and widely used, other norms such as the L1 norm and L infinity norm play important roles in many real-world applications. The Manhattan norm, also known as the L1 norm or taxicab norm, represents the sum of the absolute values of the vector's components. It measures the distance between points in a grid-based path. For this vector, the Manhattan norm, the one norm of V is calculated in this way. Consider the two-dimensional vector. The Manhattan norm of V is computed in this way. As we can see, it measures the distance between points in a grid-based path. Next, let's look at the L infinity norm, also known as the max norm. The L infinity norm is defined as the maximum of the absolute values of a vector's components. Mathematically, it is expressed in this way. For example, if the elements of our vectors are 3, minus 7, and 2, the L infinity norm of vector v can be computed in this way. It is 7. Compared to L1 and L2 norms, the L infinity norm is also computationally simple and efficient to evaluate. The L infinity norm focuses on the most extreme value in the vector. That means if just one component is large, it dominates the entire norm. For this reason, the L infinity norm is especially useful in worst-case analysis, when we care most about the largest deviation. This makes the L infinity norm valuable in fields like robust optimization and the design of safe operating regions. For instance, when setting safety margins, it makes sense to account for the largest possible risk among all variables. Now, let's compute and compare the L1, L2, and L infinity norms for the same vector. Let's use this vector v. Let's compute L1, L2, and L infinity norm. As we can see, different norms produce different values for the same vector. The L1 norm sums all components equally. The L2 norm gives more weight to larger components because of the squaring. And the L infinity norm only considers the largest component. This illustrates an important general relationship for non-zero vectors. This inequality reflects the fact that the L1 norm collects the most information, while the L infinity norm focuses narrowly on the maximum value. So, the takeaway is this. Your choice of norm can significantly change how a vector is evaluated. Let's wrap up. This section began by understanding the definition and intuition behind norms. A norm gives us a way to measure the size or length of a vector, and it plays a foundational role in shaping the structure and geometry of vector spaces. Then, we focused on the Euclidean norm, the most familiar and widely used norm. We also reviewed the 4 key properties that any norm must satisfy: non-negativity, positivity, scalar multiplication, and a triangle inequality. Together, these properties ensure that norms provide not just numbers, but stability, linearity, and geometry to vector spaces. Thank you for watching. Please thumbs up and subscribe to my channel.